Diamonds come in many appealing colors which arise from an interesting physical system. Atomic impurities in the crystal have their own electrons in spatially confined orbitals, effectively behaving like artificial atoms. These orbitals lie within the large bandgap of diamond and provide electrons which are optically active. Such crystal defects are called color centers. Color centers provide optical access to individual solid-state spins and have been established as good candidates for processing quantum information. There are also excellent probes and markers in the areas of biology and medicine. In this latter context especially, there is a high demand for stable fluorescent probes at a nanoscale. The silicon-vacancy center has attracted research attention because of its excellent optical properties in bulk diamond. Unfortunately, silicon-vacancy centers in previously reported nanodiamonds exhibited broadened spectral lines and fluorescence blinking. Here we report the observation of silicon-vacancy centers in nanodiamonds with better spectral properties and give insight into the processes that lead to optical instability. These results were achieved using nanodiamonds produced through a novel technique, and the superior optical properties indicate the high crystalline quality achieved by this process. This technique is an adaptation of the high pressure, high temperature method commonly used to create industrial diamonds. The temperature and pressure simulate conditions of natural diamond formation, and the crystals are produced from metal melts containing carbon sources. Omitting the metal catalyst from this process and using fluorinated graphite led to the formation of much smaller diamonds in the range from nanometers to micrometers. Nanodiamonds from this process were spin-coated on a substrate for the spectroscopic studies reported here. A cryogenic confocal microscope was used to study the silicon-vacancy centers in these nanodiamonds at low temperatures. The spectral lines originating from optical transitions were measured with a spectrometer after off-resonant excitation with a green laser or with a photoavalanche diode while scanning a laser over the transition frequencies for resonant excitation. Scanning electron microscopy was used to determine the size of the nanodiamonds. By this it was possible to determine optical properties for nanodiamonds known to be smaller than 200 nanometers. The spectrum of the silicon-vacancy center is dominated by a sharp zero phonon line, and the ensemble line width was observed to be as narrow as 1.05 nanometer while exciting off-resonantly. In resonant excitation, single optical transitions from individual silicon-vacancy centers could be addressed, and the narrowest line widths were measured to be 350 MHz. This was an average over multiple laser scans, and the line position was found to be diffusing over a small spectral range in the timescale of seconds. Examining each scan individually suggested underlying line widths as narrow as 200 MHz, which is close to the lifetime limit. With higher intensity resonant excitation, the silicon-vacancy center also showed blinking, where the fluorescence switched on and off in a binary manner. These two different instability behaviors could both arise from electronic charge effects at the nanodiamond surface. The observation of exciting spectral properties for silicon-vacancy centers in nanodiamonds makes them uniquely attractive for use in quantum optics applications and biomedical environments.